Similarly, you can use this idea of x of t, taking the derivative of x of t to get v of t, because that's the rate of change of your position as a function of time, to get your acceleration as well, right? So, and if we look at our units, that also makes sense as well, right? Because we have meters here, we have meters per second here, and we have meters per second squared here. Because we're taking the derivative with respect to time, it's a rate per second, right? So velocity is the meters you're traveling per second. Your acceleration is your rate of change of your velocity per second, right? So that idea still corresponds there, right? So then we can also say that our acceleration, like we did in algebra-based physics, we said that acceleration is equal to your change of velocity over your change in time. Like we said with velocity above, where we said that velocity can equal dx dt, we can say that acceleration can equal dv dt. And all we have to do now is define our velocity function. So we can use the power rule like we did in our previous video to solve for that. So we can use x prime of t, which is also equal to v of t. It's just calculus notation, to get 6t plus 2. But now we want v prime of t, or a of t, to get 6t 1 minus 1. And then since the 2 is a constant right here, we can just say that like all constants, if you take the derivative of them, you get 0. Because what a derivative is really saying is what's the slope at that instant, right? And if we just have a straight line, the slope is always going to be 0. So for all constants, your slope is just going to be 0, right? And then so for this particle, in fact, we can say that the particle's motion as a function of t is always going to be 6 meters per second squared.